As a second example, we could look at this data set from SNEE's study. That was a data set that unfortunately had no replication involved, or no replication in it. But I can still do something here. What I'm going to do is ignore the last factor. There are factors A, B, C, D, and E. So we've got A, B, C, D, and E. And to do data analysis, I ignore the last factor for the time being and pretend there were only factors, the first four factors, and do an analysis, go through the Yates algorithm as if there were only the first four. And so what I've got listed here are the data values from SNEE's study in a particular order. So let's look at this order over here and think about what I've got there. Look at the first row. As regards the first four factors, A, B, C, and D, where are those factors set? No, they're all set at their low level. That would be, you can ignore the presence or lack of presence of E all along here, okay, because I'm simply concerning myself at this point with the first four factors. What I've got here is Yates order for A, B, C, and D. I'm ignoring E. If I did run through the Yates algorithm, so I'm going to use a 4-cycle Yates algorithm. Okay, 4 because 4 is 5 minus 1. What comes out of the 4-cycle Yates algorithm are these values. Those values are made with a 16 divisor, not a 32 divisor, but a 16 divisor, because in terms of doing data analysis, I temporarily ignore the last factor. Okay, and now the question then is what to make of these values in that last column. If there were no factor E, that would be the grand mean. But it's not the grand mean, it's the grand mean plus whatever is aliased with the grand mean. And I'll remind you that the defining relation for this SNE experiment is this. It's I is indistinguishable from A, B, C, D, E. That's the grand mean plus the 5-factor interaction. Okay, if there were no factor E, this would be what? Well, it would be the A main effect. But it's not just the A main effect, it's the A main plus anything that's aliased with it. So this is plus B, C, D, E 4-factor interaction. Let's think about this guy, for example. If there were no fifth factor, that would be the A, B, C, D 4-factor interaction. but since there is a fifth factor, it's not just the ABCD four-factor interaction, but the four-factor interaction plus whatever is aliased with it, and what's aliased with it is the A main effect, and so on. So the point is that I run through the Yates algorithm, I get these guys, but then I have to interpret them in terms of what these what the pattern of aliasing or confounding is in this setup here, in this half fraction. So I don't have any replication. I can't make confidence intervals, but I can do normal plotting, and here's what I get if I make a normal plot of these values. And basically this picture suggests to me that even if most of the things that come out of the Yates algorithm are essentially noise, there's probably at least one and maybe as many as four of them that are more than background noise, and as a matter of fact those correspond to four main effects and their corresponding alias four-factor interactions. Hopefully, if the world is simple, essentially those things can be attributed to the main effects. So all I can do is make tentative conclusions because I don't have the full 2 to the 5th factorial. But looking back at this thing, the point that is furthest from the line is that D plus ABCE point, and that would suggest that the most important factor is factor D, the reactant purity. The second most important one is this guy, because he's the next furthest from that line that I've drawn in there. It's the second biggest sum in this table. So what I'm pointing out to you is that the biggest guy in this table is here, except for the overall mean. The second biggest guy is there, followed by this one, and then this one. And so in order of decreasing importance, it looks like I might say factor D, B, E, and A, their main effects are the most important effects, possibly the most important effects in this experiment.